This is example 15.2. We're going to talk about this one in the example problem section. We're also going to talk about 15.8 in the example problem section on how to solve 15.8 in terms of, actually it's number 6, 15.6, in terms of how to solve this problem using the formula method. Then we're going to talk a little bit about the principle of superposition. That'll come up in the examples movie. The next method for calculating deflections is called the moment area method. And we have two theorems that provide a non-calculus alternative to calculating these deflections. What I have to say about this is that the formula methods is easy, okay? And some of the diagrams, some of the problems we use are fairly easy. When it comes up with asymmetrical loading or lots of different loads, then we end up using the moment area method because it's a little bit more involved. It's a little bit more robust for us to calculate stuff. So we're going to be covering this example. Okay, so what we have here is we have a beam that's loaded, we have a shear diagram, and we have a moment diagram. And now the first moment area theorem says this. We have these two angles. We have an angle from B to the elastic curve. So this is a tangent line from B to the elastic curve. This is a tangent line from A to the elastic curve. And then the angle between these tangents of any 2 points on the elastic curve equals the area of the moment diagram that lies between the 2 points divided by EI. Now, finding these areas can be easy sometimes. They can be a little bit more involved in some cases. And we've got different ways of dealing with that. But in formula form, here's what the first moment area theorem looks like. That's theta, which is the angle between any two tangents on the elastic curve. It's in units of radians. Remember that 1 radian equals 57.3 degrees. A sub m is the area of the moment diagram lying between the two vertical planes that pass through points A and B. The basic units are pound inch squared or Newton meter squared. E, again, is the modulus of elasticity, and then I is the moment of inertia with respect to the neutral axis. So this gives us the angle between two tangent lines. There is a second moment area theorem, and it essentially talks about deflection. Okay, so in this particular case, what we have is we have a tangent line to the elastic curve at point B. So here's our elastic curve. This tangent line is at point B. This tangent line is going to intersect this plane A. And where that intersects that's where we're going to call the deflection, y from A to B. So essentially that is the deflection from B to A. It's not necessarily a deflection, it's just a deflection of the tangent line. So the vertical displacement YAB of a point on the elastic curve from a tangent to the elastic curve at a second point, point B, equals the moment of the area of the moment diagram that lies between the 2 points. Taken about the first point, point A, divided by EI. So what does this mean in terms of a formula? Here it is. So YAB is the vertical displacement of point A on the elastic curve from a tangent line drawn at point B on the elastic curve, equals A sub m times x bar. Okay, so A sub m is this area of the moment curve between points A and B, and then x bar is the location of the centroid of that area from A. Okay, so the distance from the centroid of the diagram between any 2 points A and B to the point where the vertical displacement is desired. So that's the second moment area theorem. We're going to be talking about some of these examples in example 2 because that's really how I go about showing you how these things work. There's one more thing about this, and it's moment areas by parts. Okay, so for instance, when we look at this moment area, so this moment area got pretty complex. We're going to talk about this one in the examples. But anyways, you got a triangle, and then you got a rectangle. So the areas, calculating those areas and their centroids was actually quite easy. But it can get difficult. If you have like a distributed load, for instance, then your shear diagram is like an angle, and then you got second order parabolas down here for your moment diagram, in which case you're going to have to calculate areas and centroids of second order parabola shapes. Okay, so it can get cumbersome. So one of the ways to get around that is to do moment diagrams by parts. Okay, this is what is shown here. Okay, in this case, what we're doing is moment diagram by parts at point B. So every time we have a point load, we got a reaction at A, and then we've got this load at B, and then we also have this distributed load here, 3 kips per foot. So we have like 3 different things, 3 different force systems that are causing moments about point B. Okay, so what happens is the moment of reaction A about reaction B starts at 0, where that load is, and then it increases up to 300. Now what's 300? 300 is this 15 kips for RA times this 20 feet. Okay, so that's essentially the moment. So as you approach this point B, your moment increases. Now, where this 10 kips is, what we have is a 0 moment at this point here, but that increases to negative 150. Negative because the load is pointing down. The 150 comes from the 10 kips, as shown here, times the distance to point B, which is 15 feet. Okay. And then over here we have 3 kips per foot. That's where we have this parabolic area right here. And that gets to 150 feet. So this would be another way to do it. What we're trying to do is make our lives simpler using the moment area method by dividing up the moment diagram into the 3 different components. And again, we'll discuss this in the example problems.